Okay.
Yeah. I was just saying, I just thinking as I was collecting notes for today that it's really seems like it's so valuable to have a conversation about this material. Um, I'm just imagining reading it for the first time could be uh, could be hard unless you've seen a lot of this before. So I really want to talk about this with people. Hey, Tanya. Hi, Christopher.
Hi.
Okay. I'm glad you
Mm.
guys can make. So let's see. I even have a board to use. I don't know. Let's see if this works. Okay. Maybe. Maybe it might work. Let's try. All right. Someday people will figure out how to do this telematic stuff better. Hi, Stephen. Okay. So let's just start right away because I'm starting the recording now so that we can keep video notes for people. Just a quick check-in. Last week on Maturana and Varela, and this week are actually connected. I hope you can see. So I was wondering how you guys been doing with extracting some of the ideas from Maturana and Varela, and this week from Kaufman. Some things that stick or some things that are particularly mysterious. Let's register that right now. Chat. You'll rush. Oh,
I didn't get a chance to do the readings discussion last week, but this week I've been having actually a really interesting time reading. I've been listening to the videos, and I've read most of the readings from Kaufman this week.
okay.
And I think he has some really, really interesting ideas. I think about the way we um, view. I think what he's trying to get at is like the way that physics informs our view of biology, right? I think that's what he's trying to. I think he's trying to dissuage like a an attitude that like a physics mindset can have when we think about life. I think
Yeah, two
kind of
things:
the.
computers, physics. Yeah,
Well, can you repeat that?
computers and physics, two different big mindsets that he's trying to detach a little bit from, or not detach, to get beyond. The word is beyond.
Yeah, it's like
Yeah.
it's like he wants us to like it's not like he doesn't like the thinking. It's like he doesn't want us to put our thinking in a box based on these things. Yeah.
Got it. That's it. Put your finger on it. So thank you very much. Okay, that's the key takeaway from these 2 weeks. All right, and there's a fellow named Giuseppe Longo who and we talked to, and he's actually coming to. Well, he came ready to give some talks, and the way he put it, the way Longo put it, he's a computer scientist, but Longo, a mathematician, um, worked a lot of foundations in computing, kind of really hardcore stuff. And then when he came to give some talks at ASU some years ago, he, he put it he put it very well. He said, "Look, it's not that physics is wrong, computer science is wrong. It's more that it's not all there is to it." So basically, the way he put it was um, physics conditions life, but does not determine it. And I think that's a great way of thinking about all sorts of frameworks like computer science. You can say that computers condition our modern life, but they do not determine it, and they shouldn't determine it. They can't and they shouldn't. Um, So that goes for all sorts of schema. That's kind of the spirit for all this kind of the reason why I'm introducing these different ways of looking at things. The metabolic, Autorana for later autopoietic, and now with Kaufman. And just to give a little bit of background, Kaufman started a huge advance in understanding evolutionary biology, kind of the biggest change since Darwin, because he started using complexity theory and automata theory and what looked like very formal models to try to give other ways to think about how life gets more and more complex, more and more rich, just based on the opportunities, the combinations that are possible when you get more molecules together or more chains of molecular processes together. And he describes it in a video, in one of those two videos, I think, pretty well. He's a very engaging person. And it doesn't have to do with telos, like, things have to aim to a final form, nor does it have to do with, and it's more than just, how do you say, blind chance. There's chance involved, but it's not blind in the sense that every time some new feature comes up in some organism, like the heart muscles pumping to pump blood, there are these ancillary possibilities that open up that other organisms or the body itself can take advantage of that were never there before, kind of as a side effect. And everything happens by side effects. It's pretty, very cool. And there's more and more side effects. So that's kind of a crude way of putting it. Anyway, what other things that people got from the past week or this week?
There's a quote I want to read out. It says, sorry, let me bring it up. The living world is not a machine, deducible by Laplace's demon, for whom the world was deducible, given Newton's laws and the current positions and momenta of all the particles. So this is in chapter 11, A World Beyond Physics. I think, just like you're saying, the way I kind of understand it is like, so physics obviously is important and does give some explanation, but it almost seems like biology accounts for the context. So when he was explaining how Peter, Gus, and Sly, doing that entire thing about, it's this Peter stuck to a rock and all that. There were some things that, like you said, are not blind chance, but then you can't, there's no equation, right? And so it makes me think about how people interpret data, where it's like, this is what the data says, right? But then context a lot of times is as important as data, because in different contexts, data means different things. So yeah, I'm going to link this to like climate change, but the idea is that we can be looking at geospatial data and clearly say that, maybe there's deforestation somewhere or a river has shrunk somewhere, but we can see that as people who don't live in those regions and say, okay, so this is what has happened. But then if you're on ground and you have the context, you may realize that it's not as simple as, climate change just happened. It may be that someone actually diverted the water from a water body to another place. So while, yes, it's true that water has shrunk, what's also true is that the cause is not always apparent. So it makes me think about data and the importance of context. So it seems to me like biology gives some context to the physics, that the physics of like life and, evolution.
There's something very subtle going on in these passages that Licky is pointing us to. It's worth looking at later yourselves. These notions that he's bringing in from like this thing about niche creation, all that. It's worth looking at later on. But I'll just jump to the middle of this chapter here. I'm highlighting some really key points. There are 2 points. This yellow one's 1 point, and in a minute, I'm going to highlight the next point, which is in the next sentence. So a couple of things to think about there. And I'm still trying to wrap my head around it, okay? If you think about any feature like the heart pumping blood in a mammal, or the way the bird's wings are feathered, or the gallbladder. An example that's used is the gallbladder of a float bladder that's in a fish that has evolved in a certain way for certain to be able to be part of the metabolism of the fish. Turns out to have a side effect, which was to afford more buoyancy to the fish, because I guess from the way that metabolism worked, that maybe the float bladder in the fish happened to have more gas, or at least less dense material in it. But that lower density or the gas also made the fish float better. So it was actually, very helpful. But it didn't appear because it didn't appear because the fish needed to float better. Okay, it happened to be a side effect that made the fish float better. And this kind of side effect is what the biologists like Stephen Jay Gould, who was one of the great biologists around this a bit before Kaufman, have been pointing out, that this is what it's been for billions of years. Okay, so it's really interesting. So it's not random, right? In the sense that, oh, well, the creatures then take advantage of it, and not just bouncing around. So this brings us to the story that's in one of the links here about Patrick and Rupert. It's very funny. I'll show it to you later on. Well, maybe I'll go there now. Okay, but don't let me forget. This is one point, okay, which we can explore in just a minute. And the other point is this one, which is in this sentence here. Oops. That the ecosystem, let's say, or an organism, any kind of life, we can never say about that creature or that ecosystem ahead of time what all the possibilities are for that creature or for its descendants or for the future ecosystem, what those options are. We can't pre-state the set of all possible futures for an ecology, ecosystem, or for a species. No way. And this is radically different from physics. Radically different.
Okay. When I have read these types of thoughts and thinking about this deterministic nature and how physics, wants to write these deterministic rules, right? When I thought about this idea that you can't, the prediction is impossible. I guess this is kind of making that statement, but it's saying we can't state the phase space. But it felt to me when I was first learning about this that the reason is that we can't make a perfect measurement, right? And so due to the fact that we cannot make a perfect measurement, that's where we can't predict, because these very tiny differences that we may not be able to measure, right, would be the thing that would. And so this is kind of, so that's like palatable to me. I can understand it. And maybe I'm guilty of, I always want to look at the math, please. And this is kind of in saying like we can't do the math. I
You're raising three really big points. I'm trained in math, right? So it's really big challenge to mathematicians. Okay, but I'll get to that point. It's actually a very profound challenge. Okay, but going to the first point about prediction. So what Tanya's talking about, right, goes under the word chaos. Which I think is a terrible word because it's just too big a word for what it describes. But to be more precise, is what Tanya is saying, right? You have basically, it's a matter for even if you have a complete equation, like it can be a quadratic, x squared plus 2x plus b, whatever, ax plus b. There can be even equations as simple as that if you iterate them, get the answer, plug it back in, do it again, plug it back in, do it again, iterate. Even such simple, fully deterministic systems, you have the equation in front of you, just crunch the numbers. You might, if you there's under some conditions, some choices of coefficients, you can, it can happen that you can compute one value for given initial seed value. It goes through different values, and you can vary that, just to repeat what we heard just now, by a small amount. So on 1.0, instead of 1 exactly, it's 1 plus delta, where delta is a very small number, arbitrarily small. And yet, if you iterate that, it goes wild. The values you get just cycle out. Okay, this is well known. If you write computer programs will do that. Okay. But the key thing is it's called unpredictable, get chaotic behavior, etc. But still, the key thing there, it's still a deterministic system. You have the equation in front of you. So if you plug in the same value exactly, you will get the same results back. Now, what's an indeterministic system? Non-deterministic system. Well, maybe you can think about this. If you're writing a program, and the program, in fact, is an algorithm. Typical program is a deterministic system by definition, right? If you plug in exactly the same input, you get an answer out. You get the same answer out. If you don't, then something's wrong. Computer's broken. Except, how would you introduce that kind of behavior into a piece of code, practically speaking?
You could like, I guess the only way that I can think of is if you had like a piece of that program that basically gives the syntax to ChatGPT, right? And ChatGPT can like rewrite the program to make it run differently or better in the next iteration, as opposed to this iteration, something like that.
Right. Yeah. That's yes. But then if you enlarge the frame, then in ChatGPT, it is in fact a very large program, and it has code that will, that will tell it to, under these kinds of inputs, do something. So, it's still deterministic. Okay. In fact, there are rules that tell it how to make variations. Okay. So it can say, for example, this input has been put in twice by the same users, so don't give the same user the same answer. In fact, generate another answer based on this algorithm, right? So that's still a deterministic algorithm.
I think what that answer does is it just makes the box super big, right? It makes the field that the billiard balls can bounce around like really big. But what we're trying to do is like remove the walls. Right.
Even before ChatGPT, programmers since the beginning of programming, have had a way to introduce this kind of non-deterministic behavior, actually.
Randomness?
That's it. Randomness. Just throw dice.
Yes, but the random generators are deterministic.
Yes. That's why it's called pseudo-random. It's not really random. because the random number generator really has a seed in it, as I think Tanya's going to point to, right? The seed can be something, can be like time of day, right? Or seed can be, if you want to be really fancy, the seed would be a quantum generator, quantum bit, something from a piece of hardware. Like with the radioactive isotope decay. I mean, that's how they really do it. They build little like radioisotopic decay things, a little Geiger counter that counts blah, blah, blah. It counts up a certain number from the real analog world. That's the key. True randomness comes from analog world. It does not come from von Neumann architecture, Turing equivalent computing. Does not. It's by definition, actually. This is just by construction. Computer programs of this conventional type can never be random, actually. So that's why it's called pseudo-random. They just have a big table, basically, of numbers. It's a finite table, your limit of memory, and just jump into some point and start indexing along the table and get a sequence of numbers with uniform distribution. But if you jump into the same seed value, you get the same sequence out. So it's not really random. Now, okay, so that's pseudo-random. Now we go to I gave you the hint to get true randomness, where there is no way to repeat, basically, you go to analog. Now, what Kalf is talking about is even more open than that. And this is where it gets really profound, okay? Because what he's saying here, well, okay, the way he tells it in a certain place is the following. He says, I tell you guys to think of a hammer, okay? And then I ask you, can you think of all the ways you can use this hammer? Let's try it right now. We have 4 people here. Just shout out, hammer. How can you use hammers?
You can break a window.
Break a window. What else?
You can open a bottle with the
Open
back.
a bottle on the other side. Couple more.
Drive a nail.
Drive a nail, open a bottle, break a window.
Smash a watermelon.
Smash a watermelon, hammer a sword, bang, bang, bang. You know, I'm a smith. How about a more outrageous? I mean, more inventive, less obvious.
You can knock pine cones out of a tree.
Okay, you see what's going to happen. Okay, and I'll give one more. I sing the song. If I had a hammer, I'd hammer in the morning. Well, that's a hammer too. They say, "Hey, you're cheating." It's a song. That's a word in the song, right? Or you know, to hammer on an idea, to hammer out a grant proposal. Right? So what's really interesting about this is that, and then he said to you, and then he says to his audience, like, can you feel your mind going blank? If I asked you to think of all the possible uses of a hammer, that's not even a set, actually. This is his basic point. First of all, it's not enumerable, meaning if I have one use, there's no successor function that will tell you the next use. Like the integers are enumerable, okay?
Right.
It's not countable in that way. It's not a countable set. But it's not even a set because it's not even clearly understood what's in or not in that set. And furthermore, it's not determined in a very profound way in that the more I ask you, the more we go into the world and ask people, the more answers we're going to get. And not just the more answers in terms of what can be counted, listed, but the more types of answers we're going to get. More types. Like going from a physical tool to a word in the song. That's a change in category. Right, etc. So there are going to be uses of hammers that don't even exist today that may become uses of hammer in the future. So that's a very profound type of indeterminacy. Okay, there may even be a future in which people won't know how to ever respond to that question anymore. So the hammer becomes what disappears from the universe? What does it mean when people can no longer answer the question? So this is what he means when talking about pre-stating the phase space, is that in physics, when we have a physical model, a mechanical system like 2 pendula, you know, bang, 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 like this. So you can write down the position momentum of each pendulum at any point in time. So you can write the equations of force acting on it. And then you can say, what are the possible configuration spaces of this 2 pendula? And then for each configuration, like this swing and this swing here, there's an energy associated with this versus this. Straight down is least energy, tilted out is a little bit more energy, more potential energy. all that kind of stuff. But you can specify, in fact, you have to specify in advance the configurations and then specify in advance the energies associated with each configuration. And then away you go, you do physics. You can solve those equations, et cetera, et cetera. That's how physics works. But same thing, economics, neoclassical economics, right? You have to say, in advance, one poses in advance, these are the consumers, these are the producers, these are the products. Each products have a set of prices. Consumers have a set of utility functions. I will buy this at this price, but it goes higher, then I won't buy it anymore. So there's these kind of price functions. And then you solve neoclassical economics, you do the math, you solve these constraint equations, and you get these solution sets. So if the prices are within this region, then you will have consumers that will be agreed to buy these products at those prices. So that's called the solution set for an economy, classical economics, okay, which is basically a branch of convex mathematics. However, with people talk about disruption, right? So new services that never occurred before, like Uber, comes out. And how did Uber come out? Well, these are side effects of internet, of having cell phones, smartphones, people, So in just a few years, bang, disrupted. Okay. So some people, myself included, think that in social technical worlds like societies, markets, language, biology, we can't pre-state ahead of time instead of all possible states. There's some math behind it too. Let me show you some pictures, some equations. So this is a picture of animals from Stephen Jay Gould. I mentioned him before. He's one of this. He was one of the really popular, famous, super communicative biologists at Harvard. And he had this funny chart. Let's see, how do you read this? This is like two snapshots in time. The top one is earlier in time, and the bottom one is kind of after a few billion years or a few 100 million years of evolution. So let's say a couple billion years ago, if you look at the complexity is a horizontal dimension, and body mass, the amount of proportional living matter, okay, is the vertical, okay. So that's to read the graph, the way to read the graph. And in the Precambrian times, up to the Precambrian times, I guess that's a couple of billion years ago, you can see most life was not so complex. It's toward the left end of the complexity scale. And so it's mostly bacteria, basically. But after a couple of billion years, we have seen in the fossil record a lot more variety of complexity of structures, morphological structures, etc. So that's why this big hump, has spread out to include much more complicated multicellular organisms, such as Brontosaurus and Homo sapiens. Okay. Now, just to be clear, this graph is a little bit vague. What it really means is up to the present. Okay, not just the present. That's why it has dinosaurs. So makes sense? Okay. So and this is the observational fact from looking at all the records. And this paper which looks at from just looking at complexity and how things evolve in time. Or maybe I should show you the same graph but a different. Sorry, let me take this off. Okay, I'm going to kind of skip all the equations and just go to the picture that you get from studying these kinds of what happens when the phase space itself, the space of possibilities, gets more and more. Remember the story earlier about how organisms have side effects, development features have side effects, then other organisms can take advantage of the side effects. So those kind of second order, third order accidents can actually yield more and more complexity in the ecosystem. Okay, I'm just using words to skip over a lot of math, but the words are what's important because words give you the actual logic. The math is a way to make a model to simulate that, okay? But anyway, I'm going to share with you the result of some mathematical models of that idea. Right now, share. Here we go. And try this. Okay, so here's the result. So the way to read this is the following, this picture. It's a bit more precise than the previous one, using these kinds of diffusion equations to model how a set of an ecology, let's say, occupies more and more of possible states, more and more possible states emerge over the course of evolution. So if you have a coarse measure of complexity, complexity can be measured in different ways, which can talk about another time. 0 over here, you see the 0 in the bottom right here is time. This time axis. It's kind of fun. It goes from 20 back down to 0. I guess 20 is, I don't know what 20 is. 21 units of time. This is abstract measure of time. So starting as time 0 is way over here on my right-hand side, okay? Bottom right. And then it marches forward in time, sliding down to the left, okay? The other axis, which is really important, is the complexity axis, which is on the left-hand side, okay? It goes from 0 complexity out to more and more complexity. And the most useful axis, besides time, is the vertical axis, which is how much body mass, what percentage of mass, biomass, is, for a given time, is represented at a certain level of complexity. Okay, so in other words, the bacteria are way over down near the 0 part of complexity, let's put it this way, single cells, okay? But this is at the beginning of time, which is here, okay, 0, time 0, in the simulation here, most of the biomass of living mass is clustered near this low complexity end, okay? That's what big red spike means. And most of so very little of the biomass, if you look down to an increasing complexity, is 0, close to 0. Okay, but now let's march forward in time under the diffusion process. 0, 4, 8, 12, 16. Okay, see what's happening to the distribution. If you look along a single curve, along a single slice of time, like time 12, let's say, or even time 20. Okay. You see what's happening to that curve that used to be really peaked at low complexity? Can you sort of imagine what's happening if you take time slice by time slice with the distribution of mass? Can anybody see?
It's kind of like the distribution is like, well, at first it like very rapidly evens out, but then it more slowly evens out over time, and like higher complexity beings sort of inflate more of the biomass than lower complexity beings as we get closer to T20.
It's interesting, isn't it, that if we just look at the along the low complexity end, which is this plane, the vertical plane in the back of this cube, right? There's a peak at the beginning of time, but then apparently under this model, okay, not every model, yes, it's true, more of the biomass flows out toward it's distributed along the more complex types of organisms, but it does increase a little bit over time, you know. So it's a way of thinking, if we think about the actual evolution on Earth, it seems to reflect let's say hypothesis, we'll say, that it may be that single cell organisms themselves, or quote lower complexity organisms themselves have proliferated too over the billion years. There may be more biomass now than there was, I don't know, 500 million years ago of single cell organisms, because that what do you call it, that family has also proliferated too. Okay, that can happen. But the key thing is that there's a general distribution of biomass toward more and more complex types of organisms. Okay, and this happens all the time. Always, whenever there's a lower bound on complexity. In this case, lower bound on complexity is 0. So it's a mathematical fact. Okay. So it's very powerful, these kinds of arguments. Okay. So it doesn't really, so it's a qualitative but rigorous statement. Okay. So these are the kinds of things that people are talking about in current biology, theoretical biology. And also, some people, we are porting some of these ideas over to thinking about economy, language, social structures, etc. Okay. Any ideas here at this point before we move to another bunch of ideas? Okay, so let's hang to that. Now, another thing I wanted to bring up. See if did I forget something? Yeah, here is people talk about the origin of life and all that kind of thing. So it's still unclear, right? We don't know. We're not there, so we can't detect it, and we don't have many observational models out there beyond Earth. Not now, I mean. But it is interesting to think about going back to Maturana and Varela. And I'll make this point in the announcement ahead of time. It's more than just saying the thing self-reproduces. It's more than that. That's what Maturana cannot say it. Maturana and Varela were pointing out. You need a system. You first have a system with our parts like lungs, heart, liver. Also some processes that maintain each part. But also relations among the parts. And then what makes a system autopoietic is this continuous renewal of the parts, but also the relations themselves have an invariant relation among them. So second, third order. Okay. And I think I mentioned this last week in our session, but I think it didn't come through from reading the text. Okay, these are these extra characteristics of what makes something wonderful. So if we move to this week with Kaufman, what he also was called the MacArthur Prize. MacArthur is this award for, kind of so-called genius award for very, people made a lot of contributions in the arts and science and all that. So he got one a long time ago. And part of what he got it for was, it was this idea about adding on to this idea about what makes something living, is this idea of kind of a self-containedness of metabolism. Like people talk about examples. I don't know, what examples did you guys use for, or maybe Stephen or Tanya? I remember Licky's, but Christopher or Tanya, what examples did you guys use for autopoietic organisms? Or Licky also, I can't remember all of them. They're interesting. What were your examples for autopoietic organisms? I know some of you brought up viruses or computer viruses, or I think another one was hydroelectric system. What else?
I talked a little bit about computer viruses. I gave a couple examples and then talked myself out of them as I was writing. Like each of my examples, I was like, this might be one, except for this thing.
It's hard.
But yeah, every time it was also hard because it was, they were like defining my terms was difficult, right? And so we were talking about non-biological autopoietic systems, and that became difficult because the definition that they gave in the writing. I mean, for them, they were like, it's definitionally a living system if it's autopoietic in their argument. So it was
Yeah.
hard that there are systems that like might appear to be autopoietic, but behind a lot of those is interactions with human beings.
Yeah.
Or
Yeah, key. You know, that Stephen mentioned FDM programming systems, and that's something that's why I mentioned earlier about the general model for computation is Turing computation. Okay, I'll just put it down in here in the chat. Going to make sure I capture the Turing model of computation. Because all algorithms, absolutely all programming languages basically used in conventional digital computing, okay, are formally equivalent to a Turing program. Okay, and you can look it up. And then Turing programs in particular, then you can go look at Turing programs, Turing language, Turing programming languages, Turing model for programming, for computing. It's a very basic model. And then look at the what they can or cannot represent. Okay, so that's to get a track. And that's why earlier I talked about how these are deterministic systems, and they don't contain the non-deterministic behavior that we observe in living systems. Okay, just shortcut. But some other models could be like, I actually think, well, one issue with the program, okay, is that a conventional program stops, meaning you give it something, you say go, it computes things and it stops. That's, if it doesn't stop, then it's in a loop. That's, I mean, an error condition. It's a loop. Or
I think that's why I was thinking about computer viruses, because once they've been released, they are self-replicating.
And that's another thing. Remember in examples that, you know, a chicken laying an egg is not an autopoietic system. It's producing another object. And a car factory making a car is another example of a system that has parts, sure, but doesn't reproduce itself. And viruses can make copies of themselves. But the interesting thing is how the chicken reproduces, maintains itself. The word reproduce is used in two different senses, so that's confusing. So what's interesting to think about the car factory or a computer program and how it sustains itself, you know. And this thing about Talos, right? So the other thing that's really interesting, I think, about computer programs is that a program is interactive, is waiting for input from somewhere, from another program or from a human user. Therefore, in its operation, it has inputs and outputs in the very way it operates. So that's another hallmark of it not being a autopoietic system. It's not really autonomous. Now you can push back and say, hey, wait a minute, you know, animals, we eat, right? We eat and we drink and all that. So we take in stuff, right? However, I think this is where it took me a while to get my head around it. Yes, of course, the system always has to bring in energy, but much more of this thing about how is operating on its own. Yeah, sorry, how is operating in its own to maintain itself, okay, in its own operations. And that's where the submarine example is helpful. And also, it's a point of view. From some point of view, I can regard the chicken as an autopoietic organism when thinking only about its internal metabolism. But if you think of it as producing an egg, then it's allopoietic. So it really depends on point of view.
The chicken itself is, but also there's a system of chickens, and that incorporates laying eggs. I thought about this when I was thinking about bees, because I was trying to find a way to think about a system that incorporates non-living aspects, right? And I thought, okay, there's bees as individuals, and bees as individuals are one thing. They certainly have cells and they become themselves all the time, but they're also a component in this wider system. So in the wider system of a beehive, the bee itself is not autopoietic, right? It's allopoietic, yeah.
Yep, it's a very, very, very profound point Tanya was raising. And in fact, that's one of the big powers, I think, of thinking this way is to also take into account not just point of view, but scale. Where do you draw the boundary? For any question, where do you draw the boundary? Okay. Does it include me in that account? Right? Does it include us in that account? That's yet another way to think about boundary. The people who are talking about it, are they included in the theory or not? Okay. So that's what some people are doing with what's called second order cybernetics. There's cybernetics, which is about systems and thermostats, like I mentioned a couple of weeks ago. But what's called second order cybernetics is when you talk about this kind of idea of a system watching itself, like a thermostat and a thermometer, right? And regulating itself, when you include the theorist in that account. That's when it gets really interesting. It gets reflexive. So let's put that aside for now. Okay. Now, the thing about, well, this brings in this idea of closure, actually. How do you draw the boundary? And Kaufman and other biologists thinking about this have been thinking about all sorts of, well, 3 different ways of thinking about closure. Okay, closure of what? And I think there's a very interesting, more sophisticated way of thinking about closure in terms of what's called catalysts. Anybody heard of this term from chemistry? What's a catalyst from chemistry? I'll draw a picture.
It's I think a chemical that helps molecules approach equilibrium faster, I think.
So you just need a small amount of you can add a small amount of chemical to help things move along. Just even sometimes just in small, tiny quantities to help catalyze a chemical reaction where larger quantities are involved. And then what's really the beauty of this catalytic chemical reactions is that you get that small catalyst back often. So you can reuse it to stimulate, to trigger further chemical reactions, other chemical reactions, for subsequent chemical reactions. So, and it's used over and over again. I mean, we see these examples in many different everyday situations. Okay. This diagram I'm putting on the screen is about a different kind of closure, but I'll use this diagram also for talking about catalysts. It's similar, not exactly the same, but similar. Okay. But the C here in this diagram refers to constraint, but just allow me to kind of reuse the diagram where C stands for catalyst, okay? But the idea is something like the following. I wish, I could draw it on the board. That's probably better. Should I draw on the board? Yeah, how about I draw on the board? Hang on, instead of trying to reuse the thing. So, but can you see if I draw something like this, oh, you can't see that. I'll actually, you know what? I can try to, well, okay. Can you see A0 plus A1, 2 chemicals, and then it yields A3? Okay, all right. So, all right. So, for example, if you do this, you might have to add some, heat. All right, so boil the water, boil the 2 chemicals together and just add some heat. It may be that it requires a lot. Requires a lot of heat, okay? What you can do sometimes is add the catalyst to this situation and may require much less energy to make this thing go, okay? If you're lucky, you have to determine that. And what you get back out is like catalyst back out. Okay, so actually the diagram should look more like this. Okay, catalyst goes in, combines with the 2 reagents, you get the result back out, A2, and you also recover the catalyst. Great. And then you use it over again. Now, suppose we have a bunch of these kinds of reactions. I'll have to redraw this diagram. So A0 plus A1 goes to A2, and then catalyst 1 goes in, it comes back out. Okay, yeah, okay. We have other reactions. You might have something like A3 plus A4 goes to A5, okay? And then Right, okay. Now, here's the trick. Here's the key thing. This result, A2, maybe A2 sometimes serves as a catalyst for something else. So maybe A2 is actually C2. So A2 actually is C2 and catalyzes another reaction. Now, what was really amazing is that there were simulations that were done. See, you can say, well, this can go, but this is enclosure, it doesn't go back. But if it does loop, what if, for example, this produces A5, right? And what if A5 is actually the catalyst you need for the first reaction? Now you have a kind of a loop going. Now you have to be really astronomically lucky to have some two chemical reactions that do this, all right? Don't expect that. What's really amazing is that this is the thing that Kaufman was talking about in modeling and conjecturing, is that living beings are characterized actually by what are called autocatalytic sets. These sets of metabolic processes that generate catalysts that are needed for other processes, and they close up. It's close. It becomes closed system catalyst. Amazing, actually. And so there were first some software simulations, actually, to say, well, how many processes do you need to have before enough of them will have a chance of generating catalysts for each other, where you have closure. And turned out that, I can't remember, it wasn't that many, maybe hundreds, not millions. In other words, the numbers were small enough to be feasible in the course of molecular evolution on the planet Earth to have happened a lot, actually, a lot. So no need for Darwinians, as a complement to Darwinian selection. Amazing. This is why he got the Nobel. Why he got the MacArthur Prize, Kaufman. Okay, and with a lot of other people working with him. All right. All right. I drew the diagram on the fly, so it's kind of messy. Apologize. So let me go to this picture. Okay. Any comments for that right now?
I'm just thinking of, this is making me think of things that I've read and thought about in terms of synchronicity. Like when there's something, there'll be like, there's this chemical reaction and I can't remember the name of it, but where it just like, once it starts, it just keeps going and going and going, like back and forth between two states. And
yeah,
that's all I have.
Yeah, there are. I think it's called liquid. There were liquid crystals and chemical clocks. I can't remember way back, but now they use them. It's amazing. Liquid crystals were an example of these kinds of systems that would cycle back and forth between colors and things like that. So yes, there are actual physical models for these things. Now this closure of what's called auto. You can look it up. I'll type it into the chat. The keyword is auto. Catalytic sets. Okay, that's the keyword. Now, there are other models too. You can even have closures. Remember, talking about constraints, physics can constrain. You can also have sets of constraints too. And I will just mention it, but won't go into it now too much, but I'll just mention it. So let's take a look. Share screen, picture. This diagram that I just shared earlier is similar idea, but the C's in this diagram here don't represent chemical catalysts, they represent constraints. And we don't have time, we're running out of time now, but I do recommend you can look for what's called constraint closure. Those of you who want to go deeper into this kind of issue can look into what are called constraint closures. And this is a lot more subtle. Okay. All right. And this is where we can, I think, begin to migrate from models of metabolisms in animals to models of other kinds of systems like economies. All right. So I'll just leave it at that for now. You guys are very brave to step into this, but this is really kind of some of the deeper resources that we'll be drawing on for this semester. Okay. All right.
Okay.
Any last questions for now? All right. So do enjoy the card. He has a very nice story called the remarkable true story of Patrick and Rupert, the world's first single-celled predators and prey, in cartoon form, which tells the story, the real story too, but in a more graphic manner. Okay. All right. So enjoy that, and look forward to your replies. Take care. Bye bye.